Hi guys, so today's video is part of the preparation of series. In this video, we are going to go through a comprehensive list of all of the ways to prepare alcohols, including diols and geminal diols, which you may have learned under the name of hydrates. So this video is going to be pretty long because there are a lot of ways to make alcohols, and I'm hoping I include everything, but if I don't, let me know. Anyways, because of that, we are not going to be including mechanisms in this video, so any reaction that you see that you want a mechanism on, please let me know in the comments below. Alright, let's get started onto the video. Okay, the first way we're going to talk about making alcohols is the SN1 mechanism, which you should be pretty familiar with because it is one of the first reactions that you learn in organic chemistry. It works on secondary and tertiary substrates, although it does work best on tertiary substrates, and it occurs in a product solvent, and in this case, to make an alcohol, water is the nucleophile. I have two examples I'm going to show you on how to make different types of alcohols, and in both cases, chlorine is our leaving group. Of course, there are many combinations that you can have to create an alcohol, but water is the nucleophile every time. Following SN1, we have SN2, another substitution mechanism. Of course, SN2 is a concerted process, whereas SN1 is not. SN2 reacts best on methyl and primary substrates, but it does react on secondary substrates as well. It occurs in a polar aprotic solvent, and in this case, water or H3O+ is the nucleophile. As you can see, it makes a primary alcohol in our first example, and in our second example, we are doing a ring opening of an epoxide. And it does create a diol, so this is also a way that you can create diols. Acid-catalyzed hydration is one of many addition reactions that can produce an alcohol. Water is added across the double bond in the presence of a dilute acid to the most substituted position. Many professors will allow you to write this over the arrow simply as H3O+. It is important to note that in the event a chiral center is present, the products will be a racemic mix, meaning that there will be an even mixture of both enantiomers present in the products. So you can write this as plus enan or racemic mix, either one depending on how your professor is. Oxymercuration-demercuration is another addition reaction that produces an alcohol when water is added across the double bond. This is Markovnikov addition, so the alcohol goes to the most substituted position, but it occurs without carbocation rearrangement because mercuric acetate will dissociate to become the very powerful electrophile, the mercuric cation, in step 1, and this ensures that the most substituted carbon never gets more than a partial positive charge, so rearrangement cannot occur. In the second step, sodium borohydride will remove the mercury and allow this product, the alcohol product, to occur. So what's important about this is that in not every reaction you will get the selectivity that you need. So if you're looking at something from a retrosynthesis standpoint, you need to know the subtleties and differences between all the reactions to know what reagents you use to get to where you got. I'm not sure if that makes any sense, but I know there are a million reactions and it gets overwhelming, but the conditions, the little differences, really make a big difference on what you get. And that is pivotal. It is pivotal to understand that to do well in retrosynthesis. So yeah, keep that in mind. Hydroboration-oxidation is another addition reaction that produces an alcohol. It is unlike the first two we went over because this results in anti-Markovnikov addition, so our alcohol will be on the least substituted position and our hydrogen will be on the most substituted position. So this is important if you were trying to make something like a primary alcohol. It is another good condition to understand for retrosynthesis and synthesis strategies. It is also syn addition, so in the event of a chirality center, this means that both the hydrogen and the oxygen that were added are either both on a dash or they're both on a wedge because they face the same way. They are syn addition. I have 2 examples for you so you can get the full effect of how this reaction works. It is, again, another important strategy to understand the subtleties of, which I'm sure by the end of this video you're going to be going insane by how many times I have said understand the subtleties for synthesis strategies, but I'm going to keep saying it anyways. Reduction reactions are next. Okay, we have about 4.5 different ways that you can make alcohols from a reduction reaction. I said 4.5 instead of 5 because one of the methods isn't quite different enough to be its own method, but there are still some differences. So now we are going to go in detail for each of these methods, what you need, and how they produce different types of alcohols. Okay, so method number 1, you start with either an aldehyde or a ketone, and the reagent is molecular hydrogen with a metal catalyst. The need to know of this method is that it will reduce other pi bonds, so other alkenes or alkynes present in the starting compound will also be reduced all the way down. So you'll see with the examples I'm showing you right now, the starting compound is different. In the top one, we don't have any double bonds besides the carbonyl carbon with the oxygen, but in the bottom one we do have an alkene. However, we get the exact same product. This is true for all products of this reduction method. It reduces all the way down. Okay, method number 2 also starts with an aldehyde or a ketone. The reagents are sodium borohydride with water or an alcohol. The need to know is that sodium borohydride is a weak reducing agent, so it will not react with the alkenes or the alkynes. This allows us to maintain some selectivity and control in our products. If we use the same starting material that we used in the prior method number 1 example, you can see that our carbon-carbon double bond is maintained throughout this reaction. This is very good when you are trying to decide what type of alcohol you want to create. So again, it works with an aldehyde or a ketone, and this is great when you want a little bit more control. Okay, method number 3 is specific to the carboxylic acid functional group. It is really important when you are trying to keep other carbonyl groups present but also add an alcohol. It will only react with the carboxylic acid functional group. So let's say you have a compound that has other carbonyl groups present and a carboxylic acid functional group, and you want an alcohol. Well, you can use this method to ensure that your other carbonyl groups are not touched at all, but you still get your alcohol. It is very, very good for providing some additional control over the reaction to produce the product that you want, which is maintaining the other carbonyl groups, but removing the carboxylic acid to create the alcohol. Okay, method number 4, your starting compound is either an aldehyde or a ketone, and the reagents needed are lithium aluminum hydride in step 1 and water in step 2. Water is your proton source. So keep in mind, this is not a concerted mechanism. Please remember to write the numbers by your reagents. This is not concerted because if you tried to have this all happen at the same time, it would explode, so don't do that. It is important to keep in mind that lithium aluminum hydride is a stronger reagent than sodium borohydride, but it won't react with your alkenes or your alkynes, so you can still maintain that sweet control over this reaction. Okay, method 4.5 has a bunch of additional starting products that you can use, and the reason it's not its own method, in my opinion, is because the only major difference is that this must happen in the presence of excess lithium aluminum hydride. Otherwise, the reaction will not occur. Your byproducts will vary. For example, if your starting compound is an acid halide, your byproduct is going to be an acid, in this case HCl. Of course, your byproducts don't really matter because that's not what you're looking for, but it's just important to keep in mind. If your starting product is an acid anhydride, then your byproduct is going to be a carboxylic acid, because the group, your leaving group that comes off does get protonated. Protonated? Wow, I'm really proud of my pronunciation. That's what happens when you talk to yourself for a long period of time. Okay, yeah, I'm just going to leave that in, whatever. Okay, now the star of the show, the one you have all been waiting for, are the Grignard reagents. I'm sure that you have been taught so many times that this is the most important reaction you will learn in organic chemistry too, but there's a lot of important reactions you learn. This one's just pretty special because it makes alcohols and grows the carbon chain. There are two different ways to employ this reagent. Of course, it's basically the same mechanism. It's basically the same thing. It's just one different step. In way number 1, you can use ketones, aldehydes, or epoxides. And in way number 2, you can do acid anhydrides, acid halides, and esters. Of course, remember, you need your Grignard reagent and your diethyl ether, your BAT, in step 1, and your proton source in step 2. Okay, let's get started with way number 1. You know, in step number 1, you are going to have your Grignard reagent and your little BAT, your diethyl ether, because this cannot have any acidic hydrogens, or this reaction will not occur. So in step 1 of way 1, you have your Grignard reagent and your diethyl ether. And then in step 2, we have our water, our proton source, which will produce our alcohol. And I have a few examples for you. I have an example where we use a ketone. And look at our pretty alcohol I love this one. It looks like a little weird person. Not to judge anyone, but it does. It kind of looks like a weird, creature. All right. The other example I'm showing you, we start with an aldehyde, and we are adding a methyl group via Grignard reagent. So this is still making an alcohol compound, although it is adding R groups. So I am actually leaving out a few types of alcohol preparation reactions if they involve the addition of things other than R groups, which make things more complicated, and I couldn't really classify directly as alcohols. So just keep that in mind, that this obviously adds other functional groups besides just alcohols, but R groups, alkyl groups aren't usually the priority group pretty much ever anyways. So yes, and then the last one is with an epoxide that we are going to see. And I liked to make this one a little bit complicated so it would look pretty. My markers also started dying on me for no reason while I was doing this, which was very frustrating. But, it happens. All right, so yeah, I showed you an example with a ketone, aldehyde, and now an epoxide, and we grew some great creatures. Okay, way number 2. The only thing that is different about this from way number 1 is that your Grig, I call Grignard reagents Grig, sorry if that annoys you, your Grig must be in excess. Basically, this reaction happens twice, so you are going to add 2 of whatever your Grignard reagent is. So instead of just growing it by 1 R group, you're going to be growing it by 2 R groups, your carbon chain. So this will make an alcohol, and in this case, you see we have an acid halide, and it will become a tertiary alcohol. Never forget your little BAT, guys, your diethyl ether. Never forget him. So as you see, we are now going to install 2 R groups, and look at that creature. Look at that beauty that we just made. Okay, I'm weird. And we have a few more examples for you as well. And I'm going to stop talking so I don't keep saying weird things. All right, let's go. Okay, so we're going to move on to diols now, but I just wanted everyone to keep in mind that there are technically other ways that you can make alcohols, but in those processes, you're also going to be adding other functional groups, which is where things get a little bit confusing with synthesis, and I didn't want to include those in this video because I very much wanted to focus just on adding alcohols. Of course, I did just show you Grignard reagents, which add other R groups, but that's a little bit different versus adding like halides and such. So everything in this video only involves R groups and alcohols. Okay, moving on to diols. Okay, anti-dihydroxylation is the first one I'm going to show you. Your starting compound is an alkene. This is an addition reaction. Your reagents, it occurs in two different steps. In step one, you have a peroxy acid, commonly either peroxyacetic acid or MCPBA. In step two, you have H3O+, your addition source. This is anti-addition, so you will get a trans diol. This is because in step two, it is an SN2 process, so you have an inversion of configuration. That is what produces the trans diol instead of the cis diol in this reaction. Next step is Syn-dihydroxylation, which is just like anti, except it's nothing like anti because you get syn addition. This is because both oxygens are added at the same time, so there is no SN2 step, which is what created the inversion of configuration. And instead, we have three different reagent options, which is OSO4 when it's catalytic in the presence of NMO, and we have option 2, which is two different steps, and option 3, which has to happen under cold conditions. And again, whenever there is a chirality center present, you have plus enantiomer unless it's a meso compound, in which case it's a meso compound. Okay, now we have reduction of diketones, and given how much information I went in on reduction methods for just regular alcohols, I just kind of wanted to keep this one brief and show you three different options. I'm pretty sure you could do this if it was like two aldehydes or a ketone and an aldehyde. I don't really think it matters, but I've only ever used it with diketones. So three different ways, but that's it. Okay, another way to make diols is, let's say for example, we have a compound that already has an alcohol on it, like the one I just drew for you, a primary alcohol that also has bromine on it. What we can do to use the Grignard reagent is if we protect the alcohol, so that way there's no acidic hydrogens for the Grignard reagent to react with, we can make a Grignard reagent. We will protect the alcohol in the first step, and basically the hydrogen comes off and you have the OTMS instead of alcohol, and that just like preserves it. Then we can make this into a Grignard reagent with Mg and then our diethyl magnesium, and then diethyl ether, our little bat, and then we can treat this. We have a ketone here is what we're going to attack, our carbonyl, so that's our Grignard reagent process. And then we are going to get this funky looking thing. And in the final step, what we do is we now deprotect the alcohol. And there are a few different methods of doing it. I just am giving one example here. TBAF, this will pull off the TMS and you are left with a diol. So that is another way to create a diol when you already have an alcohol. Okay, the last thing we're going to go over is geminal diols, also known as hydrates, which you probably learned them as hydrates, even though that's an incorrect way to classify them because it's not specific enough. A hydrate is anything that has had water added to it. A geminal diol is when you have two alcohols attached to the same carbon. So just writing out examples of these for acid-catalyzed and base-catalyzed pretty much looks like the exact same thing in regards to reagents. The difference comes down to mechanism with acid and base catalyzed. I don't know when you would actually make these because these are generally unstable compounds, but I decided to include them for you anyways. I hope you enjoy. All right, that is it for this video on surviving organic chemistry. But before you leave, keep in mind that this is part of a series. So look in the description box and see the other functional groups I plan on making a part of this series. Let me know in the comments below what you want to see next, what you need to see next for anything regarding organic chemistry, gen chem, physics, math, genetics, cell bio, any field of biology at all. Leave a comment, leave a like, help a fellow college student out by subscribing to this channel if you found it helpful. Thank you. Have a great day. Good luck studying. I believe in you. You're probably amazing. All right, bye.